Imagine that you just moved to a new city, and you're looking for a really good place for a meal that's close to your new home. As you just moved to the new location, you obviously do not know anything about where a good place to eat is, so you decide to ask for a recommendation. Now, you have two options. Would you rather take a recommendation from your next door neighbor, or would you rather take a recommendation from a random person in the same city but lives 30 minutes away from you? Without knowing any other information other than where they live, I bet most of you chose your next door neighbor. Why? Because since they're local to the neighborhood, you think they must know some good places, or at least better than someone who lives far away. Algorithmically, you're more likely to like something if someone else who shares something in common with you also like something. In simplified terms, you think closer equals better. In this example, the thing you shared was location, but it doesn't have to be physical proximity. In your day-to-day, you see recommendation systems like people in your area have also liked this, or others who have purchased this item have also purchased that, or this song is popular among others with similar tastes, and so forth. One of the models based on this concept is called nearest neighbors, and that's what we're going to talk about today. So let's break down the idea of nearest neighbors for a second. Think about the three examples I just laid out. All of these have the same pattern, which is those that have something in common with you chose something, therefore I'm going to recommend the same thing to you. In other words, the prediction of the unlabeled data point is going to be just the same prediction as an already labeled data point nearby. Do you notice something about this method that is fundamentally different from everything that we've discussed in this channel so far? You can see that with nearest neighbors, there isn't actually a function that is trained to learn various factors and uses those to predict a label. Rather, it simply finds the nearest neighbor and then returns its label. There are no parameters in which the model learns from. These kinds of models are called non-parametric models. As its name suggests, there are no learned parameters. It just knows other examples. And of course, everything we've done so far falls under the parametric models. Like in a simple linear regression model, the model predicts using the best fit line, which is essentially made up of these parameters. Okay, so nearest neighbors sounds simple enough, so let me give you an example. Suppose you have this data that looks at the person's age, how much loan they took out, and whether or not the person defaulted on the loan. So in the test data, you have this new loan application of someone who is 31 and is taking a loan out for $125,000. And you're tasked with predicting if the person is likely going to default or not. So you decide to use a nearest neighbors logic. But how do you define who amongst the training examples is the closest to the person in the test case? You have this person who has the closest loan amount, but you also have this person who is closest in age. So you can quickly see that we need some kind of a distance measure so we can actually calculate how close a test case is to the training examples. This is where it gets interesting. Typically, when someone thinks about distance, they think about the Euclidean distance, or the L2 distance. This is the same distance as what you're familiar with, the distance formula. And fair enough, Euclidean distance is a commonly used distance metric in nearest neighbors. And then you have the Manhattan distance, which, as its name suggests, is a grid-like distance, and the Minkowski distance, which you can think of as a midway between the aforementioned two distance metrics. To be honest, I haven't run into any instances where Manhattan or Minkowski was needed. However, one metric that can be used and is quite popular in other machine learning models is the concept called cosine similarity. This is the dot product of 2 points divided by the norm of each of the 2 points multiplied. I won't go too much in detail here, but cosine similarity is a measure of strictly the angle of the two vectors, not their distances. You might think why we would care about the angle more than the distance, but in higher dimensional space, the distance starts to degrade in meaning, and the similarity or the cosine angle between the vectors becomes much more meaningful. I'll elaborate on this a bit later. In any case, a distance can be calculated between the test data and all of the existing examples, and the test data is labeled with the nearest neighbors label. This is the idea behind the nearest neighbors algorithm. Now, let's add a bit of complexity to this by finding the k number of closest neighbors. In other words, when a test case is given, find the closest k number of existing data, and then maybe do something like return the average over the k number of labels. So then, the test cases label can be determined with multiple examples, not just one. This makes the prediction much more reliable. Visually, this smoothens out the decision boundaries of the labels, and naturally, as you increase k, the boundary becomes smoother. This is k nearest neighbors, which is the real nearest neighbors algorithm that is used over the simpler version. Now, your question is, how do you choose k? Well, if you haven't learned the theme throughout machine learning yet, here we go again. Choosing these parameters is the art behind machine learning, and there's no definitive answer. However, one concept that is worshipped in the field is the concept of Occam's razor, the idea that the simplest is usually the best. Choosing a small k means that the predictions are going to be more sensitive to noise because the prediction only relies on a small number of neighbors. But if k is too large, boundaries become blurred, and the model may start to lose meaning. You want k where you can clearly see distinction between the predictions while also staying simple. The guideline to use is to start with a small k and then increase the k value as you see fit. The good thing about machine learning is that you can always try and adjust your parameters. K nearest neighbors is a simple, intuitive model that is really easy to work with, as it's a non-parametric model that doesn't require training. Despite this, we don't actually see a lot of KNN being used in practice. I showed you a few real-life applications at the beginning of this video, but even in those scenarios, you're more likely to see applications that use other models. That's because nearest neighbors algorithms have a major problem that it's not very scalable. Consider the example I showed earlier about predicting whether or not someone is likely going to default based on age and loan amount. This is a fair example, but it only considers two factors. A real bank is going to decide based on many factors. And for every additional factor, there's an additional dimension to consider. This means that in the case where we have to deal with many dimensions of data, calculating the distance between points is going to require much more computation, and not only that, as you increase the dimensions, distance itself kinda loses significance. It's already pretty much impossible for a human to even visualize distance when the dimension becomes anything above the third dimension. How would you even calculate, let alone interpret, the distance when the dimension is something more like 27? This becomes way too computationally expensive and hard to interpret. This is why we like to use the cosine similarity, because this metric doesn't consider the physical distance, and the vector angle is much easier to compare when dealing with high-dimensional data because we only care about the directional differences. But even then, KNNs are not very efficient with large and complex data, so it ends up not being a very practical one, unfortunately. Thankfully, there are other non-parametric models that are much more efficient, important, and practically useful. Over the course of the next few videos, I'll be tackling some of them, so stay tuned.